Section 9.1, Introduction to Probability. So probability is looking at what are the chances that some event occurs. So let's say we're tossing two coins, and we want to know whether we have no heads, one head, or two heads. And we often would think that it's going to be a third for each of them, but that's not actually how it works. We've got a little tally thing there to kind of give you an idea of when that might happen. But that's really not how it works. It's basically going to be a fourth, and then a half for one head. So when we talk about probability, we want to say random. We're going to hear that word a lot. So we assume everything is fair. We're assuming that all of the outcomes are equally possible, assuming, of course, that they are equally possible. So we were talking about the heads and the tails if we toss an ordinary coin. So with one coin, we assume that head is equally as likely as tail, but of course it's random, so we don't actually know which one it's going to be. And again, we're going to take out any weird things that are going on. We are assuming that we are doing everything normally to make everything fair and random. Alright, so when we talk about what are the possible outcomes, that is our sample space. So this is everything that could possibly occur, and then event is a subset. So if I'm flipping my coins, heads and tails are going to be my sample space, and again, the event, for example, might be getting heads. So how, in general, are we going to get this probability? Our formula is we'll take the total number of outcomes in that sample space, and then the number of outcomes of that event. And this is another way of expressing that exact same formula, slightly shorter notation there. So let's look at a deck of cards. An ordinary deck of cards, we have 52 cards. We have 4 suits: diamonds, hearts, clubs, and spades. The first 2 are red, the second 2 are black. And then there's 13 cards in each. We've got 2 through 10, and then the jack, queen, king, and ace. And jack, queen, and king are called face cards. And do note we are assuming they are thoroughly shuffled. In other words, the order is random. So first of all, what is the total sample space? Well, that is going to be 52. We've got 52 cards total, and so that's our sample space. So what is the event that the chosen card is a black face card? So remember, our face cards are jack, king, and queen, and 2 of our suits was black. So in other words, there are 6 possibilities total, and we've kind of got a little shorthand notation so you can see those there. So then, what is the probability that if I randomly choose a card, I get a black face card? So my formula, again, I'm going to take the total sample there on the bottom of 52. On the top, I've got the chances it's an event, which we said was 6, and 6 over 52 is about 11.5%. Let's look again at just counting those elements of the list, because sometimes that can be kind of hard to do. How many integers are there from 5 to 12? And again, you can think of them, I'm counting 1, 2, 3, and so on, so we would have 8 there. That one's a little bit more straightforward, but in general, we do want to be very careful to make sure we are counting correctly. Let's generalize that. Let's say here m is less than or equal to n. How many integers are there from m through n? So we're going to express n as m plus n minus m. And the m plus 0 is the first element, m plus 1 is second, m plus 2 is the third, and so on. So the element m plus I is the l plus 1st element. And so the number of elements in that list will be n minus m, but then we do have that little plus 1 at the end. And that is a good theorem to know as well, because we will see problems like this in our homework. So let's see an example of that. How many 3-digit integers, in other words 100 to 999, are divisible by 5? Now, I don't want to count those because there's an awful lot of those. Again, you could mentally picture it out as trying to find each of those. And they're kind of showing there how to find every fifth number, essentially. So first of all, how many are there total there? There should be 180 integers that are divisible by 5. And then let's find probability. What is the probability that a randomly chosen 3-digit integer is divisible by 5? So the total number of 3-digit numbers is going to be 900. Again, I'm using my little theorem there. And we have 180 from our previous problem. So 180 divided by 900 is going to be 1 in 5. And if you think about it, well, every fifth number is divisible by 5. So hopefully that answer does make sense.